Hello, welcome back. In this video, we're going to learn about ionization chambers, a way of measuring dose. Now, recently I came to this place. This is actually one of the largest sundials on the earth. It was built in the 18th century and it still works today. It can measure the time of day to better than 2 seconds. Really a remarkable feat and very simple device. So we're going to look at kind of the medical physics equivalent of this, which is a chamber, which is really in essence a very simple device, wires and voltages and charges, and it can be used to make a measurement that you can very accurately determine the dose in the patient. So I'm going to go through that in some detail. So let me start here, and I'm going to start by drawing a little sketch of the ionization chamber, and we'll go from there. So let me start by drawing two metal plates as a cartoon, and I'm going to connect them and apply a voltage between these two plates. And I'll draw it like this, a negative and a positive terminal, and that connects the two electrodes, and that will allow you to collect charge inside this chamber. Inside the chamber is just air typically, and it's usually at the ambient pressure and temperature of the outside atmosphere. And then inside the chamber are going to be charges. These are electrons that are going to be made in ionization events, and the electrons and photons come through. So they're attracted to the plate because of the voltage gradient. There's a force on these electrons, makes them flow towards the anode. And then that charge is collected on the anode. And if you leave the beam on for a certain amount of time, you collect a certain amount of charge. And that charge is going to be written with the symbol Q. That's a standard nomenclature. Remember that the units of that are coulombs, C, or typically nanocoulombs would be measured in a therapy beam. So that's the typical range. Okay, and another thing to note then is that this chamber doesn't sit out in air, it's not just floating around. It's in some medium, either water or plastic, and then you're measuring the beam in that. So a photon comes in, interacts in this medium, it Compton scatters and makes an electron, or scatters an electron into the chamber, and that's what you measure for the charge. So the formalism that describes this is called cavity theory, or Bragg-Gray theory, named after the developers of this. And under this theory, basically the situation is that the beam is not perturbed, disturbed by this little air cavity and chamber in it. And so under those conditions, you can take the charge that's measured and convert it into a dose. And in the next video, I'm going to go over in detail how to do that. But before we get into that, I want to talk about some practical chambers and how they work. So I'm going to start with one particular important type of chamber here. This is called the Farmer chamber, after the person who invented it. And you'll see it's a cylindrical geometry. It's called a thimble chamber sometimes. The active area is down here. I'm going to focus in on that. So let me draw a diagram of that. And here I'm drawing the little air molecules that fill this air chamber in here. The central electrode here is held at a high voltage, so let's say typically 300 volts. And then also the outer electrode in black, that's like a conductive plastic, and that's here typically held at ground, or 0 volts. And so you'll see there's a potential difference of voltage between these two electrodes, and that's what allows you to collect the charge. So an electron comes in, creates plus and minus charges. The minus charges, the electrons, are collected on the anode, and you read that out here. That's the charge Q. Now, of course, as I talked about before, this thing usually sits in some medium. So modern chambers here would be waterproof. You stick them in water, and the charge is created in water and comes in here. Sometimes it can also be created in the wall, and there's a kind of a correction factor for that we'll go through in the problems. So here I'm showing the electronics for the chamber, the wires that are connected, and I can kind of zoom in here. And what you'll see here, if you look closely, you've got 3 electrodes, the inner pin, and then 2 outer electrodes that are at ground. And so this is where you collect the charge from the pin in the middle. All right, and then this chamber plugs into an electrometer I'm showing here. That's the device that allows you to apply voltage and also to read out charge. And then once you get that hooked up, the chamber itself inserts here into some kind of medium here. This is water equivalent plastic. And then that goes under the beam. Now under the beam, you actually put it on a stack like this. So you have plastic on top of the chamber, and so you can control what depth you're measuring at. Okay, so I showed you a farmer chamber. Here's a different kind of chamber. It's a parallel plate chamber or a pancake chamber. It's got a thin window in the front and the beam comes through that. Here's another similar chamber, just slightly different geometry. These chambers, again, will slide into some holder like this, and you measure in the beam. Now, the geometry of the chamber is like this. You've got two plates, two electrodes, and the beam actually comes down from the top. And the key to the operation of these chambers is that the space, the spacing between the electrodes is very, very small. So this could be as small as, let's say, 1 millimeter. Okay, and then so the advantage of that is that when you're scanning down, let's say below the surface of the water, let's say, then you know exactly how deep you are in the material, because the thickness here is very well determined. Now in between the two plates, of course, is air, just like any other ionization chamber, and you read the charge out from one of the plates. Actually, what these chambers are a little bit more complicated, because you have a electrode around here on either side that's a ring. That's called a guard ring, and it has a corresponding electrode down here. And that is at the same voltage as this one. And the result is that you end up having a collection area just under this inner ring, and you don't collect the charge around the outer guard ring electrodes, and that gives you a better determination of the volume. So some uses for the pancake or parallel plate chamber include measuring dose and PDDs in an electron beam. It's really good for that because you see that in the depth dimension, the up-down dimension, it's very thin, only 1 millimeter, and radiologically, since air is so 1,000 times less dense than water, it's very thin. It can also be used in photon beams. It can also be used for measuring surface dose, because you can get right up to the top where the beam comes in. So now let's go back and talk about some of these cylindrical chambers or thimble chambers. I'm showing here two of them, the farmer chamber, which we already talked about, the bigger one, and then a smaller cylindrical chamber. So you can see they're come in many sizes. So here's a summary of a few of these types of chambers from one particular vendor. And in the middle, these are drawn to scale, the diagrams. So let's start at the top here. We'll look at the farmer chamber that we've already talked about. So you'll see one of the key things is it's relatively large. So the length of the electrode here is 21.3 millimeters, 2.1 centimeters long. It's very long, and it's 6.1 millimeters of inner diameter in the air cavity. So the volume of this farmer chamber, you should know this, the volume is 0.6 centimeters cubed. So comparatively relatively large. And then now we have some smaller chambers. So we'll talk about the advantages and disadvantages of these different chambers more in a minute. But one of the key things is that a large volume chamber will give you more air, and you get a higher signal. So you get a less noisy reading, more accurate reading. So that's one of the key reasons why a farmer chamber is used for absolute dose calibration, to say how many centigrade per MU, let's say, are used in your beam. But let's look now at some of these other chambers down here. So you have, for example, what I'm calling the scanning chamber and the mini chamber. So as you'll see in a minute, these are used to scan across a beam. And the main reason you can do that with these is the volumes, the active volumes are much smaller for these. But of course, the signal is smaller as well, so that's the trade-off. Now down here on the bottom of the list, we have an even smaller chamber, the microchamber. The active area, the area where the air is 0.015 cc's, so that's good for measuring small fields, as we will see in a minute in more detail. Okay, so these are all the kind of like representative chamber types that I'm showing you now. And now let's look at how this plays out in terms of scanning a beam. So what I'm showing here is from TG 106 from APM, and this is the actual profile here. That's what you should measure. That's what's coming out of the machine. But as you scan across with different detectors, you get profiles that are different. So here's the farmer chamber, for example. This is a very large chamber, as we saw. If you use that to scan across the beam, you see the line would be like this. It would be spread out, sort of convolved with the larger detector, and the penumbra would be much wider than what it actually is. So you need to choose the appropriate size chamber for the application. And then for scanning, you want these smaller chambers like this one or this one, for example. Okay, now the other application for these very small volume chambers is for measuring very small fields. So let's look at that. Okay, so I'm plotting here the charge that's measured in a field versus the field size on the x-axis. And notice these are relatively small fields going down below 2 centimeters, and this black line is the Monte Carlo. So for now, we're going to take that as the ground truth, what it actually should be. Now, it's very important to have accurate measurement of this output as a function of field size, because that's going to determine the reference dose for these small fields. If you get it wrong, all your calibrations will be off for those field sizes. If it's too small, you will overpredict the number of MUs you should use, and you will end up overdosing the patient. You can see that some of these predictions are very low compared to what they should be, sometimes by a factor of 2 or even more. So here's the line for a farmer chamber, this light blue line. That's the 0.6 cc chamber that we saw. That's a relatively large chamber, so at these really small fields, it under-responds relative to where it should be. And this under-response is more than a factor of 2, so it's a big mistake to be using a farmer chamber for these small fields. That's just too big, doesn't respond the right way. Let's look down below here, below 2 centimeters. Let's look at this one in purple, the 0.125 cc chamber. I showed you a picture of that, and you'll see that one under-responds as well by quite a large amount. So you have to, point being, you have to pick the right chamber for these small fields. It's very, very important to do that. Otherwise, you're going to miscalibrate your dose in these small fields. All right, so that concludes this brief and hopefully useful introduction to ionization chambers. There's quite a bit more that can be said about these, so I'm going to leave you with a little bit of further reading so you can understand more details if you need to. And then now in the next video, we're going to go back and revisit this issue of how you take the charge measured in an ionization chamber and turn that into dose. See you in the next video.